Hi, this is David Delmas from Airbus, and I'm going to talk about our work on static analysis of Endian portability. This is joint work with Abdelraouf Wadjaout and Antoine Minet. A word on Endianness first. There's no consensus on the representation of a multi-byte scalar value in computer memory. Little Endian systems store the least significant byte at the lowest address, while big Endian systems do the opposite. Little Endians include Intel processors, while big Endians include Internet protocols and legacy or embedded processors such as Spark or PowerPC. Note that such conflicts might trigger religious wars, such as the civil war witnessed by Gulliver when traveling to the land of Lilliput. There, he met little Indians who insisted that eggs should be broken at the little end and fought big Indians who wanted to do the opposite. Endianness is an important source of portability errors, especially in the case of low-level C programs. Indeed, the C standard leaves the precise encoding of scalar values partly unspecified. As a consequence, the same code may behave differently on platforms with opposite Endianness. Therefore, porting existing software to a new platform with opposite Endianness can be quite challenging. Let us show this on an example. This is a small program originally written for a big Endian platform. It reads a 2-byte integer into variable x, copies x to y, and then reads y using the big Endian convention. The value is 1. Now what happens if we run the same program on a little Endian platform? Well, we get the same bytes, but when reading y with the little Endian convention, we get a different value. If we would like the same value, we need to change the code. For instance, we may replace this assignment here with a byte swap. So we read the bytes into x, byte swap x into y, and read y with the little Endian convention to get the same value as with the big Endian program. Now, if we merge the two versions of the program using conditional inclusion directives, we get a so-called Endian portable program, which ensures that both program versions read the same value for y. Note that there are other ways to byte swap x into y, such as bitwise arithmetics. This is discussed extensively in the paper, but skipped in the talk. We want to do Endian portability analysis. A program is called Endian portable if two Endian-specific versions thereof compute equal outputs when run on equal inputs on their respective platforms. In this talk, we present a static analysis able to infer the Endian portability of large real-world, low-level C programs. After the example, let us present the syntax and semantics of the language. As we may have two versions of the same programs, we deal with so-called double programs, which are composed of double statements. Double statements can be simple statements shared by both program versions, or pairs of such statements. The parallel sign here denotes syntactic difference, such as differences introduced by conditional inclusion directives. Note that even when both versions share the same statement, the semantics might be different, as assignments, for instance, might write to memory in a different way. The simple statements themselves are standard C-like statements where all left values are assumed to have been preprocessed to scalar the references. Scalar types include integers and pointers. Expressions support pointer arithmetics at the level of bytes and non-deterministic choice. There are also additional statements to express specifications, such as the assert sync statement, which says that both program versions agree on the value of the expression. Now, to define the semantics of such double programs, we simply lift simple program semantics. Simple memory states are standard stores from variable to values. Double memory states are pairs of such stores. This is the little Endian memory. This is the big Endian memory. The semantics for double statement S takes a set of double memories as an input and returns the set of possible double memories after both program versions have run statement S. To formalize the transfer functions, we leverage previous work on package analysis. To define the semantics of two syntactically different statements, we simply pair the semantics of individual statements in their respective environments. The case of test is a bit more involved. It uses the F filter here to distinguish between cases where both program versions agree on the value of the controlling expression and cases where they do not. The first two cases are stable tests and they are standard. The two last cases are unstable tests. For instance, here we compose the little Endian version of the then branch filtered by the condition with the big Endian version of the else branch filtered by the negation of the condition, and this is a dual case. The semantics of the asserting statement simply filters away any double memory which might disagree on the evaluation of expression E. In this case, an alarm is raised. This is not represented in the semantics for conciseness. The semantics of further statement is defined by standard induction on the syntax. Yet, we still need to define how memory is accessed for reads and writes. And for this, we need a memory model. At the most concrete level, each program version holds values for individual bytes. But we want to address C programs with multi-byte access to memory, and we want to compute numerical invariance, hence the need for scalar cells, which are synthetic scalar variables holding values for memory dereferences. In addition, we want to address low-level C programs, which tend to abuse the weak type system of C with unions and pointers to gain byte-level access to the encoding of scalars, hence the cells might overlap. We thus view memory as a dynamic collection of cells holding values for memory references discovered during the analysis. More precisely, a cell is a tuple with a base variable, an offset, a scalar type, an Endian S encoding, little or big, and a program version, little Endian version or big Endian version. With such memory model and any standard numerical domain, we may define a static analysis using one dimension per cell. Let us do it on the example. This represents the little Endian memory, this represents the big Endian memory. When writing the same values to the bytes of X, we synthesize 1-byte cells in both memories and record equalities in the numerical domain. Then we byte swap X into Y in the little Endian memory, which synthesizes these cells. Then we read X in the big Endian memory, which synthesizes this cell with the values computed from those overlapping cells. Then we assign X to Y, which synthesizes this cell. Finally, we read Y. We already have Y2, so we synthesize Y1. And we query the numerical domain for equality. Equality can indeed be proved from the program invariants and set constraints we have inferred. Nonetheless, we notice these invariants are quite complex and would require an expressive domain such as polyhedra. And this is not an option as we plan to scale to large real-world programs. Fortunately, we notice that many invariants are equalities, and many equalities are between the little Endian and big Endian versions of the same cells. And this is not a surprise, as we expect in a portable program that most multi-byte cells will be equal in both memories. Hence, we optimize our memory model for this common case, and we do this by sharing cells in the memory environment. We want a single representation for two cells coming from different program versions at the same memory location and holding equal values. A P cell is either a cell or a pair of cells holding equal values, which we call a shared B cell. Recall the analysis of the example with cells. We had a lot of pressure on the numerical domain. We had a double representation for memory, and we had to synthesize cells for Y1 and Y2 before querying the numerical domain for equality. Now, as we move on to B cells, we first merge the representations of memory. We reduce the burden of the numerical domain by synthesizing shared B cells for the bytes of X when writing the same values to it. And then, when reading Y, we do not immediately try to synthesize a cell for Y1. The memory domain instead first attempts to synthesize a shared B cell for Y1 and Y2 as a proof of equality. And the way it's doing it is by looking at a number of possible memory patterns, among which the following. It looks in the memory environment for any existing cell that would be equal to both Y1 and Y2. X2 is a candidate as we have this equality. Then it looks at overlapping 1-byte cells for x2 and y1, and queries for equalities. As x2 and y1 have opposite Endian S encodings, equalities are exactly these ones. Here, the success of shared B-cell synthesis relies on this abstract pattern matching and a set of equalities which can be inferred from simple symbolic propagation or a full equality domain. Evaluation. We have implemented our work on the MOPSA platform, which allows for modular development of precise static analysis for multiple languages and multiple properties. Our prototype is 3,000 lines of OCaml, and it leverages much more lines of the platform. We have experimented our prototype on open source and industrial software. We have chosen open source projects available on GitHub with multiple patches related to Endian portability bugs. We analyze small slices thereof using our specification primitives. We're able to report all portability bugs and to prove Endian portability where applicable. We also analyze 2 modules of a large prototype avionics application developed at Airbus. This application is designed to run on an embedded big Endian processor. Nonetheless, these 2 modules here are designed to be portable to Little Endian as they are to be integrated into a simulator running on Little Endian. We analyzed these large code bases quite precisely with 0 false alarm related to Endian portability. Note that the analysis of Module A was performed before its first integration into the simulator, and all findings have been incorporated into the development cycle. As a consequence, the simulation team were faced with 0 Endian portability issue when integrating Module A into the simulator for the first time. To conclude, we have presented a static analysis of Endian portability based on a novel concrete collecting semantics, which relates the behaviors of 2 versions of a program running on platforms with different Endian-S. It is based on a joint memory abstraction, able to infer relations between little and big Endian memories. We have implemented a prototype static analyzer, able to scale to large industrial software with 0 false alarms. In the paper, we also present a symbolic predicate domain, able to establish relations between individual bytes of variables in the 2 programs, such as those established by bitwise arithmetics. It has near linear cost. For future work, we plan to industrialize this analysis as a means to address avionics certification objectives related to simulation fidelity. We also plan to extend our analysis to further portability properties, such as portability between different layouts of C-types or sizes of machine integers. We also want to analyze software patches modifying data types, as we think our shared B-cell approach should be successful. Thank you for your attention.